Okay, I had a request to do a couple of problems on Chapter 5, Homework and Energy. I believe I'm going to do number 10 and number 11. So number 10 is a 2,000 kilogram coal cart rolls from rest down 50 meters uh, at a 20-degree incline. And there's a spring on the end, and what this does is that when this mass comes down here, it does have a certain amount of energy, and it compresses this spring at a distance of 2.0 meters. Okay, so let's see if we can solve this problem. What they are looking for is what is the spring constant of this spring right here. So this is a conservative problem because there is no friction. It'll be equal to the potential energy of the spring. First, we need to calculate what is the potential energy of the cart at the top of the incline right here. Now, it gives us a distance that it moves, but we need to translate that into a height. And we do that by L, or the length, 50 meters, times the sine of 20 degrees. So we can use the potential energy equation. We just need to replace H with the length times the sine of 20 degrees. So for reference, I got this up here just to remind us. And we're going to use the potential energy equation to find the total energy in the system. And just plugging in the numbers, the mass, the acceleration of gravity, the distance, 50 meters, we can use that because we got the sine 20 degrees factored in. And we have the amount of energy that we are using. So that is an important part to get to. So let's look at now the spring energy equation, potential energy of the spring. We want to solve for K. So we solve for K, plug in the values, and we just solve and we just get our answer, which is 83,750 Newton meters. And that is the answer. Let's look at another problem. A rubber ball with a mass of 0.3 kilograms is dropped from a height of 20 meters, hits a rigid surface, and bounces upward 15 meters. A, find the potential energy of the ball before it is dropped. And B, calculate the velocity when the ball hits the surface. C, how much energy is lost. So in the first frame here, we have the ball at the 20-meter height, okay? And it's just staying there, holding still. We have a potential energy. The ball is dropped. And in this case, the ball, what happens in this frame, this is a non-conservative frame because some of the energy is lost due to the ball deforming as it hits the ground. So it takes some energy that we cannot get back out. Some of it we can in terms of elasticity as it bounces back up, but we do lose some because it takes some energy to actually compress the ball on the way down. And then we have the amount of energy that's left over in frame 3 that is going to bring the ball up a certain distance. The difference between the potential energy here and the difference between the potential energy here, we're going to find is the energy lost in the system. So let's go ahead. So find the potential energy of the ball before it dropped. Well, we use the potential energy of gravity, and we find it is 58.8 joules. Calculate the velocity when the ball hits the surface. So since it is conservative, potential energy is going to be equal to kinetic energy. So we use our kinetic energy equation, and we're going to solve for V. And we solve for V and take the square root of 2 times the kinetic energy, which basically is this right here, divided by the mass, and we have our velocity, 19.8 meters per second down. And then we want to know how much energy is lost. Okay, like I said, the first time that we have potential energy here and we have potential energy here. This is our initial potential energy and this is our final potential energy. So we just take the difference, and that difference is the amount of work that went into compressing the ball we lost, and so our loss energy is 14.7 joules. Okay, thank you.